Okay. Good morning, everyone. So, hope you have a weekend. I know you have been all checking the notes again and doing the homework that you couldn't finish during the week. So, okay, you need also some relax. So now let's start the week trying to remember a little bit of what we had last week. We will divide probably this session in two, so that before the coffee, I will introduce some additional models for inelastic scattering, in particular cluster model, and the extension of this cluster model to treat continuum states. And I will introduce mainly the formal part of this, or most of this formal part, and afterwards Filomena will give you some examples, applications of this method, so it will not be all the time of this formal part. And let me start remembering a little bit of what we saw last week, because we continue in the context of this coupled channels method. So let me remind the essentials of this method. So remember that the idea of the method is that we have now a Hamiltonian describing the reaction, and this Hamiltonian contains, apart from the kinetic energy part that describes this relative motion, contains an additional term that is not written here. No, it wasn't. I didn't pick this slide. So it contains what we call an internal Hamiltonian describing, for example, the dynamics of the projectile or target. It could be also the internal Hamiltonians of both projectile and target, but here for simplicity we always consider only excitations of one of the nuclei, projectile and target. But of course in the actual process both nuclei could be excited. So imagine that we think of excitation of the target. So remember that the idea is to construct what is called a model wave function that is an expansion in the internal states, in this case of the target. If we were to include also a projectile excitation, as some of you asked last week, then in addition to these 5 functions, we could have also multiplying here some functions corresponding to the states of the projectile that we want to include explicitly. Okay? But in this case, we are constraining the problem to target excitation, so we only have contribution here from the internal states of the target. Okay? And these chi functions here, depending on the vector, the relative vector, these are our unknowns, and in order to get these functions, we have to solve the Schrödinger equation by putting this model wave function in this equation, and putting explicitly this expansion in internal states and multiplying on the left by the internal functions, we get a system of coupled differential equations. Still, you see here that there is a vector R. So this is a schematic solution, a formal solution. This is not the way in which one usually solves this equation, but it's of course it's something equivalent and probably more simpler from the academic point of view. So we have vectors here. In practice, you know, we always make an angular momentum expansion to take advantage of the fact that the total angular momentum has to be conserved. So we can separate the angular part. So the key ingredients in this representation of these coupled equations are these coupling potentials. That is where the structure information enters. So all the different models enters here through these internal wave functions. So we have to describe, in this case, in some way, in some model, the states of the target, and the interaction between the projectile and target that must contain a dependence on the internal coordinates of the target if we want to take into account this target excitation. Okay? So, for example, if this interaction is a pure Coulomb potential, point Coulomb potential, this does not produce any excitation. It can describe at most the motion of the center of mass of the projectile and target, but cannot produce excitation. We should go, in the case of the Coulomb interaction, to the dipole term or quadrupole term that produces some excitations. Okay? So this is the schematic form of the equations. In practice, as I said before, we separate the radial part from the rest, and the rest is expressed in these channel functions. These channel functions contain, I don't know if it is still with the old notation. Okay. So this is, so we have this for these channel functions and quantum numbers. We have the total angular momentum and its projection, and we have a beta that we call a channel. So a beta is, in general, a set of quantum numbers. The set of quantum numbers will depend on our model and on our coupling scheme, and depends if we are including only projectile excitation, target excitation. But you can imagine that this beta contains all quantum numbers required to specify the projectile or the target state in angular momentum representation. So in this particular case, if we are thinking of target excitation, we have one index referring to the excitation of the target. We have an L for the relative angular momentum, and we have an I that is the spin of the target in this particular example. If we want to include also the spin of the projectile, then this has to be added here in this beta channel, and then we have to think about what is our coupling scheme. For example, are we going to couple first the two spins and then the orbital angular momentum, or are we going to couple the L with the I and then, so this gives rise to different formulas, different coupling schemes, but these are just different techniques of solving this equation. So these radial equations are solutions now of these coupled differential equations in one variable, that is the modulus of this vector R, and the coupling potentials in this channel basis are now of this form. Then, to complicate things a bit more, we discussed that actually these equations, we have a set of equations for each j, because for each total angular momentum, we have a combination of beta channels of L and I, in this example, that can couple to the same j. So in practice, we have still a set of coupled equations. And so we label these solutions by not only by the j and n, but we decided to search for solutions which are also characterized by a beta. The beta beta I, this is one of the betas that we choose an incoming channel. And so our solutions are written as a superposition of the beta channels that correspond to all possible outgoing waves for a given initial channel beta I. That is why now we have an additional index in these radial functions. So we need to find n independent solutions of this type. And to impose this fact, the fact that we have an incoming beta and then all outgoing betas, in practice, this is condensed, this is expressed in this form. So these chi functions asymptotically contains an incoming wave in a particular beta, that is the delta beta beta I. So this contribution appears only for the beta that we have chosen as incoming channel. And all channels contain, in general, a final outgoing wave, H plus, multiplied by some number. And this number is what we called the multi-channel S matrix. And it is a matrix, it's a n times n matrix, because we have all possible combinations of initial and final channels, beta. Okay? So I repeat again, these chi functions are defined in this way to be consistent with the fact that we are choosing each solution to have a given entrance beta channel. And then, of course, after interacting with the target, this interaction will conserve only the total angular momentum. So the initial and final total angular momentum is the same, of course. So we don't need to distinguish between incoming or outgoing angular momentum, because it is conserved, but the betas are not conserved. So imagine, for example, that if we have a beryllium-10, this was one of the examples that you did the other day, it's a 0 plus, and after scattering with the target, it gets excited to a 2+. So this change in angular momentum has to be compensated by some change in the relative orbital angular momentum. So a way of saying that is saying that we have a transfer angular momentum. So the angular momentum is transferred from the relative motion to the internal motion, in the same way that the excitation energy comes from the kinetic energy. So we can say that the excitation energy of the projectile or target comes from the relative kinetic energy. So total energy is conserved, total angular momentum is conserved. Okay, so last week actually I forgot to put some important properties of the S matrix that we will not discuss now because it's not the topic of today, but I added this line in the new version. So one important property is that for real potentials or medium potentials, this X matrix is unitary, and this expresses the conservation of flux. So imagine, for example, a two-channel case, and so we have only two of these components, a 2 times 2 matrix. So one would correspond to same beta, so 1, 1, for example, and the other one would correspond to starting in 1 and finishing in 2, so non-diagonal 10. So this expression in this particular case is that the square of S11 plus the square of S12 equals 1. So this expresses that the flux is distributed among the different channels for same total angular momentum, and it is conserved. Of course, if we have imaginary potentials, this is no longer true because we have part of the flux that will go to the absorption. So we will have an absorption cross-section that will be reflected in this S matrix. Remember that this S matrix describes the outgoing flux. If we have imaginary part, then part of the flux is missing from this outgoing flux. It will come out as part of this absorption cross-section, but it's not contained in this scattered way. Semi-classically, so in the language of semi-classical description, one could say that some trajectories are absorbed by the target. This is a way of saying that part of the flux, sometimes some particles are removed from the elastic scattering and goes to other channel that we are not even describing explicitly here. So anything that is not contained in our model space. Or goes in the language that Filomena introduced last week, it goes from the P space, that is what we described explicitly, to the Q space. Okay, so let me proceed further. So the idea in all the models, we are not going to see again everything because we are not going to repeat the Friday's lecture, but the idea in all the models was the same. We have to identify the projectile target interaction consistent with the structural model that we are considering. So we can have a cluster model, we can have a collective model, or whatever. Then we perform this kind of multiple expansion to separate the angular part. So we have these multiple radial components of the potential. Then we have to calculate the transition potentials in some basis. So, for example, if we have the basis characterized by the angular momentum of the projectile or target, the one that is excited, then these matrix elements of this expansion look like this. Here I have used already this Wigner-Eckart theorem in the form of assumed by Boran-Mottenson, for example. That's why we have this factor here. And then we have to identify this. In this expansion, we have to identify this reduced matrix element of the potential that is written here. And this is the multiple transition potential for a given multipolarity. And this is the key ingredient, because this is what we have to give to the code, to supply to the code, for example, to Fresco or whatever. This sometimes these reduced matrix elements can be factorized, can be separated into a radial part. This is this F here, and the structure part. So in many models we have that these coupling potentials are form factor, radial form factor. This is how it is called by many people in literature, and a structure reduced matrix element. So this is very convenient when writing a code, for example, to have this possibility of separating these two parts and being able to calculate them separately. So, okay, so we saw last week the case of the Coulomb excitation, the case of nuclear excitation in the collective picture, actually only in the rotor model. And now we go to the single particle and cluster excitations. So the idea is that in many systems, and probably the simplest of one is a deuteron, it makes sense to think of this system as a combination of several clusters. Each cluster is well bound, so it's not very much excited during the reaction, but the clusters between them are weakly bound to each other. So in this way we are assuming that the main degree of freedom that is dictating, that is governing the dynamics of the reaction, is the one that corresponds to the relative motion between the clusters. But the clusters themselves are something that are almost frozen. In principle, in the strict cluster model, we don't allow for excitations of this cluster or the dynamic of these clusters. So this is something natural in the deuteron case, because as our energies, the proton and neutron, are objects that cannot be excited. This is maybe not so natural for other systems, but still can be very accurate, at least to describe part of the spectrum as low energies. So, for example, lithium-6 is well described. The ground state of lithium-6, for example, can be interpreted as an alpha coupled to a deuteron. Deuteron has a spin of how much? How much is a deuteron? Well, the alpha everyone knows, right? The alpha is 0 plus, and the deuteron ground state is? Okay, it's a 1, and parity? It's a plus, right? It's a 1 plus. This is the ground state of the deuteron. So the two spins coupled to 1. The relative orbital angular momentum proton and neutron is mostly L equals 0, 90-something%. So it's a 1 plus. So when we couple the alpha and the deuteron in the lowest, in the most economical way, this corresponds to L equals 0. And we have an object that has a spin 1/2, that is lithium-6. The same thing can be said for lithium-7. So the triton has a spin 1/2 plus, okay? And this couples to the alpha, 0 plus, and this, in this case, they couple with L equal 1, and this could produce 1/2 minus, 3/2 minus, but the ground state is actually 3/2 minus, and there is a first excited state that is 1/2 minus. This was one of the exercises that you did on Friday, and this afternoon you will go back to this lithium-7 from a completely different picture. So on Friday, we were thinking of this system as a rotor. So these two states were assumed to be part of a rotational band, of K equal 1/2 rotational band. But we can think also on lithium-7 as a cluster system, alpha and triton, and actually this works very well not only for the bound states. We can even describe the low-line resonances of lithium-7 with pretty good accuracy. So this is a beautiful way of describing a complicated system of zip bodies in terms of 2 bodies only. And typically it's good enough to describe many observables. So in this particular picture, for example, of course, we could have system with a composed of 3 or 4 or 5, but everything becomes much more complicated. So we confine ourselves to the system composed that we describe as 2 models, 2 bodies. So in the 2-body case, the projectile target interaction, so we are thinking, for example, in this lithium-7, consistent with these two-body model would be just the sum of the alpha target interaction along this coordinate. I don't write the t, but this is alpha t, alpha target, and the Triton target interaction. So these R1, R2 vectors correspond in this particular case to these two vectors. And one has different coordinates for this system. So one could use these two coordinates, but at the end, we want to separate always the projected target interaction in terms of this angle on this vector. We want to expand in this in the spherical harmonics corresponding to this vector that goes to the center of mass to the alpha Triton system. So we can express this alpha target and Triton target coordinates in terms of this center of mass coordinate and the internal coordinate. So this is convenient for what we will see now. So these are just two independent sets of variables. So we can use one or another according to our convenience. So in this two-body model, the states, the internal states of the system will be naturally solutions of this two-body Schrödinger equation, and this is something that you did already the first day. Remember those codes that Jeff gave you the first day? So you were able to calculate bound states and resonant states. So this is something that you can also use to generate the states in this cluster model. So you have to imagine the quantum number L, the orbital angular momentum, the J, and the number of nodes. And Jeff gave you actually an example, I think it was actually lithium-7, on how to calculate the number of nodes in this cluster model. Do you remember that? This energy conservation. So you had the two clusters, 0h bar omega, and then you wanted to, you go to this slide, long time ago, 1 week ago, many things happened in between, a lot of formula, but it's there. So the transition potentials in this model, remember these are just the projected target interaction matrix element between different states. So we obtain some states here. So imagine lithium-7, we get in this simple model the ground state and first excited state. So we can calculate all possible transition potentials. We can have a diagonal transition potential that describes something like the motion of the center of mass of the system. But we can calculate also, putting here a ground state and excited state, a transition potential between the ground state of lithium-7 and the first excited state. And this describes inelastic scattering of lithium-7. Okay. So this is borrowed from one of the slides of Jeff, just to connect with his notation. So I think this is, if this is not the notation, it should be very close. So I try to use a notation as close as possible. So remember that the single particle state, so we are thinking now on a system composed of a core and an additional particle. This is another case of cluster model. So imagine, for example, beryllium-11 described as beryllium-10 ground state plus an additional valence neutron. So this is the case. So in this particular example, the core has spin 0. So we have less quantum numbers to consider. So in this particular case, our wave functions, our projectile states, contain a radial part, and they contain the orbital angular momentum part through the spherical harmonic coupled to the spin of the valence particle to give a total J and N for this state. So with this notation, these matrix elements, these transition potentials, would be explicitly written in this way. And this Ni, Nf correspond to two different states of the projectile: ground state, ground state, ground state, excited state, whatever. Okay, so this is just to link with the notation that was used in the previous week, but it's essentially the same thing that we had in the previous slide. So remember, our strategy was to start from the potential, projectile target, to make an expansion of this potential in order to separate the angular part, so a multiple expansion of the potentials, In this particular case, this expansion looks like this, with this f function expressed in this way. This step maybe is not trivial for you at first sight, so maybe it's a good exercise if you try to do it by yourself. So this depends on the assuming that we have central potentials between the valence and target and core and target. So now I change here the notation, thinking on this system. So this is the valence, this is the core. So instead of 1 and 2, we are thinking of valence and core. So everything is the same. So this is valence target, core target. These are vectors, but when we make this expansion, we separate the angular part of capital R and small r's, which are contained here. So these radial factors depend only on the modulus of small r and the modulus of big R for different multiples. Now we have to compare with our general expansion. This was our general expansion. So we just identify this V lambda mu. So according to this expression, the V lambda mu are just these factors here. So the dependence of these strange coordinates, these general coordinates, is now contained here and here. So this small r is our internal coordinate in this particular model. And finally, we have to make the reduced matrix elements in the states of the projectile of these multiple terms, as always. So this is given here. Again, there is an algebra in this step, so this is not an immediate step. You have to do some numbers, not very complicated numbers, but it requires a few lines of algebra. So I write here only the final result, that just so you can have an idea of how it looks like. So it's actually a relatively simple form. So the only thing that we need are these f functions that are obtained here from once we defined our projectile target interaction. So we define our valence target interaction, core target interaction here. We calculate these radial form factors. Doing these integrals, so these are one-dimensional integral. It's a bit more complicated because we actually have to make an integral for each of these variables, so we have to make a grid on this variable, but okay, this is something that the code will do for ourselves, so we don't have to worry about that. So this is given here, and these radial parts are also the radial parts of the internal states. So this is also something that we can calculate easily. So this is the information that the code requires to do that are the valence target, core target interactions, and some information to construct this internal wave function. For example, the potential between the neutron and the core, and the quantum numbers, of course. So this is the information that we will have to provide to the code. Okay? Any questions? An example. This is similar to one of the homeworks that you will be able to do this afternoon. You will do. I see some loads. It's a simple case with two channels. So we go again to the lithium-7. So below this threshold, this 2 point something threshold, we have bound states. So we only have two bound states. The three have minus, one have minus. And so we can, in this cluster model, describe these two states, assuming that these are two clusters that are coupled with L equal 1 to produce this quantum number. I say L equal 1, why not L equal 0 or L equal 2? Could we also contribute here in this model or not? Because I said in deuteron is L equals 0 between proton and neutron, and then they combined to give a 1 plus. And lithium-6 also is, why here is L equal 1? Why L equal 0 could be possible to produce this 3½ minus state? Or not? What do you think? Actually, you see that all these states, well, you see, maybe you don't see, but I tell you these have 7½ minus and there are two phi half minus states. So they are all negative parity states. So the L equal 1 equal 0 would produce actually a positive parity state. So to produce these negative parity states, we need an L, an odd value of L. Of course, we might have this, but this will appear somewhere higher in energy. This corresponds to other configurations of the system. So if this is a negative parity state, of course, if we confined ourselves to this model of a triton 1/2 plus, a triton is something difficult to break. It's 8 MeV of binding energy, so it's a good compact object. The alpha, of course, is also a good compact object. So the only degree of freedom that we have is the relative motion. So in this model, that is useful for up to a few MeV excitation energy, the only degree of freedom, the only quantum numbers that we can control there are those relative to the relative motion. So this is something that you will not have to run to write your own coupled channels code maybe, but you will have to figure out when you try to do a calculation of this kind, what are the quantum numbers consistent with the experimental situation. So you will have to do this kind of exercises at some point. So these are results. This is for a reaction at 68 MeV. This is elastic cross-section, and this is inelastic cross-section. This afternoon you will do the same reaction, but at a lower energy, at 33 MeV. That was the same one that you studied last week. And the idea is that you compare the rotor model and the cluster model that in principle look like very different. You will see that it's possible to describe the same inelastic data with the two models. Okay. Now we go to the application of this method to weakly bound systems. So we have so far been confining ourselves to states always below what is called the breakout threshold. So we only deal with bound states. But of course, if we have a reaction like this at 68 MeV, we have a lot of kinetic energy to populate higher states. So very likely in this reaction, in the spectrum, you will obtain also some yield, some cross-section for the population of states which are above this threshold. These states are in the continuum. So in systems for which the breakout threshold is low in energy, so weakly bound system, we will have to deal in some way with these continuum states. So some of these continuum states correspond to resonances, but an infinite number of them will be just as a non-resonant continuum going from 0 to infinity. So let's see why it's important to take into account the continuum even for elastic scattering. So this is an application of this cluster model to the deuteron on nickel. This is a classical example. So consistent with our model, the deuteron target interaction will be described by some coupling potentials. If in the deuteron there is only one bound state, so in this case we have a one-channel case, and this is called, for historical reasons, after the person that first applied this is called the Watanabe potential. So in many papers they have one line that say Watanabe potential, Watanabe calculation. So the Watanabe potential is the calculation, the cluster model calculation, including only ground state, ground state. This is the Watanabe potential. So we have the proton target interaction, neutron target interaction, and this is so we have in principle deuteron is something very well known. So we can calculate a realistic wave function for this for the ground state. Also we have proton target and neutron target. So there are many prescriptions that in literature that give you accurate description of the elastic data of deuteron, of proton and neutron. So all the ingredients are in principle under control. And this is the result of the calculation for this deuteron nickel 58 at 80 MeV. And this will be the second homework for this afternoon. Deuteron nickel 58 at 80 MeV. And you see that we we make a poor job at describing this data. So clearly this model is missing something, and something very important, because this is relative to Rutherford. So when you multiply this for the Rutherford cross-section, this is a huge difference. Well. Okay, so the message from this plot is that three-body calculations omitting breakup channels fail to describe the experimental data of weakly bound nuclei. So we, even for the elastic scattering, even if we are not interested in the population of resonances of the continuum state, we will have to deal with the continuum. We cannot escape from that. This is also true for a structure, to describe the structure of a weakly bound system. So you have also interplay between the bound levels and unbound levels, so you will have to worry about what is the nature of these unbound levels. This is something that we cannot just omit, even if we are interested in the properties of the elastic scattering or the bound properties of the system. So let me go one step back. So remember why we don't have to worry about this kind of problems for a stable nuclei. So for a stable nuclei, typically they are well bound. Deuterium is actually one exception. Deuterium is an unstable system, but it is a weakly bound system. But in general, for well-bound system, the breakup threshold, like here, oxygen 16, so you have to go a few MeV in excitation energy. So in a reaction, a few tens of MeV per nucleon, the population of these states in general is weak. Well, you can go to higher kinetic energies and of course populate very high excited states, but low intermediate energies, then this part of the spectrum is not that important. You typically confine yourself to the description of the bound states of the system. But for a weakly bound system, so we come back to the beryllium 11 case, the threshold is very close to the ground state. So with a small amount of momentum or energy transferred to the kinetic energy to the projectile or target, we immediately go to the continuum. We explore the continuum states. So that is why for weakly bound system we have to worry about this, even for elastic scattering, but not for oxygen 16. So this is an example of how big the coupling to the continuum can be. So this is an application of what we will see now. So the coupled channels method. No, actually, this is not a coupled channel. This is forgot. Now we will have to delete the last sentence from the recording. Now this is an application of the optical model to helium-4 and helium-6. I think this is a beautiful example because it shows how different the dynamics of a system can be when we add just one of two particles in order we have a system that is very weakly bound. So on the left, you have helium-4 on lead at 22 MeV, and this is a nice example of this Fresnel pattern. So we are just, this energy 22 MeV is 2-3 MeV above the Coulomb barrier. So we start to have these nuclear effects. We don't have something that is pure Rutherford scattering. We have something that deviates from this Rutherford scattering, and this is a situation, this is called generically the strong absorption picture, strong absorption situation. This is just an optical model fit to the data. If we try to, so on the right, we have helium-6 data. This is actually a combination of two different experiments done at Louvain-la-Nef, and you see that it's completely different picture, situation. If you try just to use the same potential, just scaling this potential to account for the larger radius of helium-6, so you used maybe the same reduced radius but multiplied by the mass of helium-6, then you get this green line that gives you again this Fresnel pattern. So clearly it's not a matter of size in this case of the fact that helium-6 is larger, is more extended than helium-4. There is something else apart from that. And this something else that is missing here is, of course, this coupling to continuous states, or more generally, the possibility of the helium-6 to break up, to dissociate in the field of the target. So if we try to make a fit, an optical model fit, so here we are in a one-channel model, so we are not putting explicitly any channels, we are just doing a fit of the data like those that you did last week with Esfresco. We just want to get some idea of the parameters of the interaction. Then one gets something that is very unusual, that is the diffuseness parameter, that is typically for alpha particles is even smaller than from other systems, so 0.4, 0.5, 0.6. This is a typical diffuseness of the nuclear potential, and this is what you should expect in one fit, optical model fit. To reproduce this shape, you need something that is for the real part is very large, and also for the imaginary part is something close to 2 Fermi. So this is something really difficult to understand in terms of the actual range of the nuclear interaction. So this is much larger than the diffuseness of the surface of the nuclei. So what is happening here is that in this optical model fit, we are implicitly taking into account other dynamical effects that go beyond this diffuseness of the surface of the nucleus. So it is not only a structure property, what we are reflecting here in this value, we are probably taking into account through this phenomenological fit other dynamical effects. So it is a challenge for few body theories or multi-channel theories to identify what the channels are and to describe them properly in order to give an explanation of this data. So we cannot say more than that from the optical model fit. The optical model fit will not tell us what are the relevant channels. Actually here in helium-6 or lead, it could be breakup, but also it could be transfer. The neutrons will like to jump from the helium-6 to the lead target, so they very easily at these energies, so 22 MeV, these are for helium-6, these are like 3-4 MeV per nucleon, so it's a very gentle reaction, so the neutrons can easily, when they pass beside the lithium-8, jump from one nucleus to the other. So this is a process that will certainly contribute here, but we don't know. We have to look at the experimental data, assuming that they provide enough information, or we have to rely on some calculations, some putting explicitly different channels, and from this we can infer what is the relevance of the different channels to account for this effect. Okay? So the complex, we could try to extend our coupled channels method. So we already have a version of this coupled channel method appropriate for systems with a cluster structure. So imagine for helium-6, this is an example of what is called a Borromean system. It's a system composed of 3 fragments, alpha, neutron, neutron, in which the binary system, subsystems, the neutron alpha, neutron, neutron are unbound. But the 3 system contains at least one bound state. Actually, in the case of helium-6, it doesn't contain bound excited states. So the natural picture for helium-6 would be a 3-body model containing this alpha particle and 2 neutrons. But the problem, so in principle we could apply this coupled channels method. The problem is that for bound state we have a finite number of states that we can normalize, so we can calculate a wave function for each of them with one of the codes that we have been using. In this case, it would be obviously more difficult. We have a 3-body problem, so one should use phase or one of the other codes available to calculate the state of the system. For continuous states, the problem is that we have a continuous spectrum, so this means an infinite number of states that, apart from that, cannot be normalized, are not square integrable. So So the idea is to try to, in order to be able to apply this coupled channel method, which assumes a finite number of states that are coupled between them, the idea is to perform what is called a continuum discretization of the continuum spectrum. And this means to represent this continuum state or part of this continuum. So we have to identify first what piece of the continuum might be relevant according to the energies that are populated in this reaction. So this piece of the continuum will be represented by a finite number of states that ideally should be square integrable. It's not always necessary, this part, but it is for coupled channels method, it is very convenient to have also this property. So this is the idea of continuum discretization, going from the true continuum, the scattering states, to a discretized continuum with normalizable states. So this is the idea, for example, for deuteron scattering. So a continuum state will contain some radial part, some angular and spin parts. So you have here the wave function corresponding to the ground state, and this is a wave function corresponding to a continuum state. So this continuum function will oscillate up to infinity, so it will not go to zero, as in the case of on the ground state. And the fact that it is non-normalizable mathematically is expressed, this asterisk should be removed. Yeah. Is expressed by the fact that the normalization is of this, we get something of this kind, a delta function. We don't get 1 or 0. So this is also a reminder of what you already saw with Jeff on Monday, I think. So he already showed this kind of expressions. This is a possible way of getting normalized function. This is not the only way, but this is a very standard way of doing that, is making some slices of the continuum spectrum, so dividing the continuum into some sub-intervals. And so for each interval, imagine one of these intervals is characterized by momenta k1, k2. So we made a weighted average, a superposition of the wave functions. These are the radial wave functions depending on this k, so it's a continuous quantum number within this interval. This weight function, don't worry much now about it. It's chosen for different. It can be chosen in different ways depending on the nature of the continuum part that we are describing. For example, it's chosen in a different way when we have resonances. So it's chosen to emphasize some particular aspect of this continuum. But in many cases, this weight function could be chosen as 1. So you don't have to worry about this. This is just a normalization factor. So this is the comparison between a continuum state, continuum wave function for deuteron at 2 MeV. This is the red line that oscillates up to infinity, and this is normalized in order at large distances it oscillates between 1 and -1. So this is a sine or a cosine or a mixture or a combination of two. And the blue one is the beam wave function. So you see that at short distances they look very similar. Then at large distances the beam wave function starts to damp. It oscillates, but these oscillations are damp. And actually it can be shown that this beam wave function can be normalized. So the norm of this blue line is finite. So this is something very convenient, because then we can treat these beam wave functions in the same way as we treat the bound states of the system. Okay? So this is roughly the idea, and this is already contained in the slides of the previous week. So this is a schematic representation of how one in practice performs a discretization of continuum, in this case of the deuteron. So we have the ground state, and in principle we can have a continuum states in this two-body model for different partial waves for the proton neutron. So we can have L = 0, 1, and whatever. But since the ground state is L equals 0, in order to go from L equals 0 to some L in the continuum, there is an angular momentum transfer. So the larger the angular momentum, the more difficult the transition will be. It will not be easy to go from L equals 0 to L equals 10, for example. This is a huge angular momentum transfer. So we expect on this, with these arguments that only the first few partial waves will be important to describe this, population of continuum states. So this will be the most strongly coupled states of the continuum. Not all of them will contribute. So we can start making a truncation, selecting a number of partial waves. Of course, many times we don't know beforehand where should we stop. So you typically start with L equals 0 or L equals 0, 1, and 2, and then do the calculation, include the contribution L equals 3, and so on. And you check the results for the observables that you are studying, elastic scattering, for example, and see how this observable remains stable, it doesn't change when you increase when you add new partial waves. So you can do that, do this more or less phenomenologically. Then for each of these L's, each of these partial waves, we have to select a maximum excitation energy. That again, this is chosen according to the kinematics of the reaction. So if we are studying deuteron on nickel at 80 MeV, so in center of mass, this is 70 something MeV. So clearly, it will be difficult to excite up to such high energy. So we are not populating states at 100 MeV. They could be coupled, but we expect this to be small. So we make a sensible selection in excitation energy of 10, 20 MeV, whatever, and then again we have to check that this maximum excitation energy is enough for the convergence of our observables. So we select a number of partial waves, for each L a maximum excitation energy, and then for each of these truncated continuum, we divide it in intervals, sub-intervals that are beams. And for each beam, we calculate a representative wave function of the kind that we have shown before, making, for example, this average technique. So this is a continuum discretization applied to deuteron scattering. Once we have this discretized continuum, we can just apply the same coupled channels technique that we have used for bound states. There is no difference at all in the application. We have just a set of states that can be normalized. We can calculate our coupling potentials and so on. So this is just a repetition of what we have seen before for the other models. So in this particular case, the Hamiltonian, the internal part of the Hamiltonian will depend on this relative coordinate between proton and neutron. And in addition to that, we have the projectile target interaction that's consistent with our cluster description of the problem. This is the proton target and neutron target. So this is a sort of effective three-body Hamiltonian for this scattering problem. This is a description of a many-body problem, scattering problem in terms of three objects, a proton, neutron, and a target. The model wave function, remember, is expanded in the states of the projectile, in this case, of the deuteron. So this is where the discretization appears, the fact that we have a sum here and not an integral. So at the beginning, we should write this as an integral over the continuum. But this is not very convenient if we want then to write this in the form of coupled equations. So, but once we have discretized our continuum, we have represented this by a finite number of excited states, this phi n, then we can apply the same kind of procedures. And we will have a set of coupled equations with these transition potentials. So everything as before. So the observables that we can extract from this are, of course, the elastic scattering, but now we can calculate the breakup angular distribution for each of the excited state, for each of these beings in the continuum. So for this, each of these will represent a piece of the continuum, an interval part of the continuum, so we can get the angular distribution corresponding to the population of these states. And also, we can get the energy distribution, for example, as a function of the excitation energy. So it's also it's always useful to monitor this breakup energy distribution when we do the calculation, because we will see if the maximum excitation energy that we have included is high enough to describe all the states that are populated in the reaction. So this typically will show some maximum, then it will decrease. So we have to make sure that we have not cut too early the continuum. So that at the maximum excitation energy, in other words, the breakup cross-section is small enough. And then from the S matrices, that is actually what is calculated in the coupled channels, more complicated breakup observables can be obtained, and I think I don't give more details here because I think that Filomena will show you some more examples of this, so I just give you the idea. This is so the end of the story of the deuteron that we left without a satisfactory solution. So remember, we had a calculation with this Watanabe potential that is labeled here, this no continuum calculation that overestimated the data. Now, including continuum with these properties, so here we are including L equals 0 and 2. These are the potentials that I used for this particular calculation, so you can try to reproduce this. And actually, this afternoon you will try a calculation of this kind. And this is a proton-neutron interaction that was used, that is actually the same one that you will use. So this afternoon you should be able to reproduce the red line here. Okay? So the message is, as we expected, now we have put explicitly the continuum and we describe the data pretty well, so we convince ourselves that the continuum plays a very important role in the scattering of weakly bound systems, even for elastic scattering, not only if we are interested in describing breakup of the system. These are applications. As we said, the cluster model is not only useful for the deuteron, but many systems can be modeled in some way or another in a cluster picture. So typical examples are lithium-6, described as alpha deuteron. So this is an application of the method to lithium-6 on calcium-14, or beryllium-11, it's a halonucleus, beryllium-11, described as beryllium-10 plus a neutron. And this is an application to beryllium-11. I forgot to put here the references. And this is an application of the model to this helium-6 LED data that we fit with some optical model, and we found that we needed a large diffuseness parameter for the real and imaginary parts. So this diffuseness, these large diffuseness parameters, can be traced back to the coupling to this continuum state. These couplings are, in the case of heavy target, like LED, have a very long range, and this is because a main part of this interaction comes from the Coulomb potential, because we have a heavy target, so the Coulomb interaction is very, very strong, very important. So actually the dipole part, that is the first one that will be able to, the first multiple will be able to produce transitions, is actually here very, very important. And this is the main responsible from the departure of this Fresnel pattern. There's a dot line that is what one gets without including this coupling. So putting explicitly this coupling to this dipole, with this dipole Coulomb interaction, produces this strong effect on the elastic cross-sections. But I don't give here more details, because this is a more complicated situation, because now the three-body picture of this is actually a three-body. It's a three-body plus one. It's a four-body model of the reaction, and we are not going to enter into. So so much complications. Just I like it to show you this example because I think it's a beautiful situation in which you have a dramatic effect of the coupling to the continuous state. Hmm? Yeah.
Three-body cases where you consider the neutrons to be coupled, right?
The three-body CDCC. So this is misleading sometimes. So three-body refers to a two-body projectile plus a target. So this is a model. So at the beginning, people tried to describe helium-6 scattering similar to lithium-6. Lithium-6 and helium-6 have many common properties. So people try to use the same picture as alpha. In the case of helium-6, lithium-6, sorry, it was a deuteron. That is a bound system. In the case of helium-6, it could be an alpha plus two neutrons interacting with the target. But the two neutrons, at least the free two neutrons, do not form a bound state. So in this case, so this is just to emphasize that in this case, the description in terms of a two-body is not very meaningful. Because you have to define, for example, what is the interaction of these two neutrons with the target, depending on the coordinate of the center of mass of the two neutrons. So it's not clear how you cannot even measure this in practice. So maybe you can simulate with the potential of a deuteron, but this is not necessarily the same because maybe the two neutrons in helium-6 form a more extended system, like a bound deuteron. And clearly it doesn't work. So there is clearly something missing. So this is just to show that one has to go one step beyond and to go to a more complicated, more sophisticated description of the problem. Okay, so just to finish, I'd like to, to build the examples of a cluster model, you need to introduce new ingredients. I'm going to give you some indications in the case of bound states, and Filomena, after the coffee, will give you a more detailed explanation on how to include continuous states, because fortunately there is another, so you will do the calculation with Fresco, but since imagine we have a calculation in which we have to put 100 beings of this state, if you have to specify them one by one, it used to be like this in the past actually, so it is something very tough. But now there is a pre-processing code, there is another code that helps you to write in a simple way the inputs for Fresco. So you prepare the input of this code for CDCC calculation, and the output of this code will be the input for Fresco. And then you run Fresco with this input. So this will be explained afterwards by Filomena, but in many cases you are interested only including maybe lithium-7, a couple of states, so it's useful to know how to do it by hand in Fresco. So let me give you an example of how it is done, so you make also a better idea of what are the relevant ingredients that you need for a cluster model calculation in Fresco. Any question?
How do we determine weight function without omega or that in the big weight function?
How do you?
How do we determine the weight function?
Well, typically, well, I'll show you now better in the example. Typically, a Cook-Saxon potential with some, in which you will have to define some quantum numbers for this wave function. Is this how you?
Yeah, for example, in the previous slide, we have
Yeah.
In this slide, we have a 4-body CDC.
Well, you have to get the states of a three-body system. That is a complicated problem, but there are techniques to do that. You can solve what are called, for example, the Faddeev equations. This is a possibility. You can use what is called the expansion in hyperspherical coordinates. So these are complicated techniques. Probably, well, it's difficult to explain here in a few words. But there are specific techniques to solve the three-body problem for bound states or scattering states. But the most general technique is called the Faddeev equations that provide an exact solution of a three-body problem for bound states and scattering states, starting from some binary interactions and maybe a three-body interaction between them. But this is complicated stuff. We can discuss afterwards, maybe. It's a bit beyond what we are going to see. So we are not going to solve this kind of problems.
So is the way of determining the wave function is not systematic or consistent or for all reactions?
Well, you could apply the same techniques to different reactions. So you could apply these FADF equations to helium-6, lithium-11, beryllium-14, or whatever. So yes, there are some general techniques that you can apply. The problem is that these techniques are not, for example, they are not implemented in Fresco, for example. So you want to do a calculation of this sort, you have to write your own code to generate these states, or to use one of the available codes. There are some available codes like Phase, so Filomena is one of the authors of Phase, that allows you to generate the states of a three-body system. And then you need another code to generate the coupling potentials. So the coupling potentials in the two-body model are things like this. When you have a three-body model, you have 2 degrees of freedom. So in helium-6, you have the neutron-neutron coordinate, and then the coordinates between the 2 neutrons and the alpha particle, for example. So you have to calculate the same object, but in a much more complicated model. So again, you have to write some code to calculate these coupling potentials. This is something that is not, there are not standard codes. There are a few groups only working on this, so each one has its own code. 2 or 3, 2. 3, I think. 2 or 3. So they are developing their own codes. This is not something that you find easily in the market. But once you have the coupling potentials, so at least the simple part is you can read this coupling potential with Fresco, and Fresco will solve the coupled channels problem for you. So at least one of the steps will be done by Fresco or any other coupled channel code. So the difficult part, so the part where all the model is contained, is here. Once you solve this problem, the calculation of these coupling potentials, you can use any coupled channels code to solve the coupled equation. This is just a mathematical problem of solving coupled differential equations. So actually the simple part here is this, and this is the difficult part, opposite to what one might think, that this is the simple part, and solving the reaction part is the complicated part. So in this particular case, this is the difficult part. So calculating coupling potentials, just to give an idea, may take several days. Calculating the coupling equations may take 1 hour. Just to give an idea of the complexity of the problem.
So in conclusion, we had many ways to calculate the wave function in a big wave function.
Yes, there are different, of course, there are many techniques to solve the wave functions here. So in particular, in the three-body case, there are different techniques used by different groups. There is not only one technique. So you have different procedures to obtain these wave functions. At the end, all of them will have to calculate these coupling potentials in some way or another that are the main ingredients of these coupled equations. Okay, but there is not a single unique technique to calculate the three-body states of a system. Okay, we can discuss this in the coffee break. So let us think on beryllium-11, our favorite nucleus, on carbon-12, and so far we will include only the 1/2 plus, 1/2 minus, which are the bound states of this system. And this is very convenient because the beryllium-10 is 0 plus, so it could be, of course, excited, but in our two-body picture, we consider that this is a frozen object, and that all the dynamics of the reaction of this complicated 11-body problem comes from the motion between this valence particle and the core. This can be excited, it could go to the continuum, of course, but here we confine ourselves to this two-body, two-channel case. So this is the scheme. So every time you do a calculation of this kind, is good that you have in mind what is the level scheme of the system and to have a rough idea, at least an independent particle picture of the system. So in the case of beryllium-11, so you have some levels, single particle levels of this kind for neutrons and protons. So for protons you have the normal ordering of levels, but we know that for neutrons there is what is called a parity inversion of the S1/2 and P1/2 levels. So in principle, according to this independent particle picture, one would expect the ground state to be 1/2 minus, if the P1/2 were here. But in practice, it is they are inverted, meaning that this S1/2 plus is favored, and so the ground state of beryllium-11 is 1/2 plus. So in the single particle, independent particle model, we interpret our ground state of beryllium-11 as a neutron in a 2s1/2 orbital coupled to the core 0 plus, a single particle model. And the 1/2 minus will be interpreted as the population of this 1/2 minus orbital by the neutron. So the excitation here should be a kind of single particle excitation. So it makes sense to think of this single particle or cluster picture. Okay? So every time that you deal with a problem of this type, it's good to start from the very simple independent particle model to have a rough idea of the problem that we are studying. So for Fresco, the first part is common to all inputs that you have written. So you have some general name list with variables. And make sure, I emphasize here, last week, many of you started from the input examples that we gave you. And you change the potential, you run the code, and you obtain sometimes strange results, oscillations. So remember, every time you run a different case, you have to make sure that you include a sufficient number of partial waves. So in this case, I put 150 because at some point I checked that, including beyond that and that, I didn't change the result. But this is something that you have to do by yourself. So Fresco will not complain. It will run till the end. You will get some cross-section, but you have to make sure that this value is meaningful. And the same for the matching radius. So when you have a heavy system, for example, in which Coulomb plays a role, then typically you have to extend the integration up to larger distances. And again, Fresco will not complain about this. You are responsible for your results and your publications. You cannot blame on the code. And the referee will not run the code for you in general. So it will pass even the referee check, and it will be published, and maybe 3 years later you say, oh my God. Okay. Important, sorry. This iBlock variable, remember, if we are to include to couple two states, and we want Fresco to couple to all orders, we don't want to do a DWA calculation, remember also to set this variable iBlock to the number of states that you want to be coupled to all orders. So in this case, iBlock equal 2. If you want to do DWA, so you set this to 0, and you have this iter variable equal to 1. Partitions, now we need to identify in some way the structure of the beryllium-11. So for the optical model, we don't need to enter into the structure of the nuclei, but now we have to tell the code in some way that we have a composite, what Fresco calls a composite, beryllium-11, composed of some core, beryllium-10, and something else, that is a neutron. So the way to do that in Fresco, this is probably a not very intuitive way at the beginning, but the way to do that is to define an auxiliary partition. So we have our initial partition, beryllium-11 on carbon-12 with the masses and so on. So for this partition, beryllium-11, we have two states of the projectile, the ground state and the first excited state. This band P is the parity, J1/2 minus, J1/2 plus, excitation energy, CPOT, the index of the potential that will be used to describe the motion of the system in this state. Next equal to, because we are only including 2 states. Copy t equal to, because the target is the same in both states. So here we don't repeat the quantum numbers of the target. We write copy t equal 1. And then we have to define an auxiliary partition of this kind that is just to indicate what is who is our core. So beryllium-10 is the core. So this partition is defined as if you were doing a kind of transfer calculation. So removing this neutron from here, transferring it to the carbon, even if we are not going to do transfer. That is why I say that is not very intuitive, but imagine that you are doing a transfer calculation. So this neutron would go to carbon-12 to form carbon-12 plus neutron. But the important thing here is that we are telling Fresco that our core is a beryllium-10. This is the only thing why it is used, this partition, to define our core. Then projectors. Now we have to define several interactions. First, we have the projectile target interaction. So I go back to this slide. So we were saying here that the beryllium-11 carbon-12 interaction is potential index number 1. Actually, the projectile target interaction in the cluster model will be generated from the neutron target interaction and beryllium-10 target interaction. Remember that we are in this 3-body picture of the reaction. So in principle, one shouldn't need to specify a potential for this. But in practice, one has to define the point Coulomb interaction, the central Coulomb interaction between them, because this potential is actually not calculated by this folding. That could be more complicated. It is just singled out from the calculation. So this is used to define this central Coulomb interaction between the beryllium-11 and the target. So we define here just the masses and some reduced radius with this type equals 0 that is missing here because it is the default value. So this is just the central, the monopole Coulomb interaction. Then we need 2 additional potentials that are the neutron target and beryllium-10 target. And these are these 2 potentials. So using the same language of this name list style, so we have defined 2 potentials, and I have to identify them with different Kp numbers because it will be referred later on. So if this is Kp equal 1, this could be 3, or 2, or 5, or whatever. So just we have to make sure that we use different numbers for different potentials. And also, we have to generate the internal states of the beryllium-11 in this 2-body model. So these are the states of a neutron coupled to beryllium-10. So the simplest way to do that is using some central potential, maybe with some spin orbit 10. So for example, a Cook-Saxon plus a spin orbit. And this is done here in this with this additional potential. So this Kp equal 4 will be the potential between the neutron and beryllium-10. In this case, this is just a Cook-Saxon potential with no spin orbit, but we could use something more complicated than that, of course. So we have to define all these potentials. So now Fresco has the binding potential, but we have to tell also what are the quantum numbers that defined this state. So remember, in our model, we described the ground state as a neutron in a 2s 1/2 orbital coupled to the core 0+. So this is specified in this overlap name list that we haven't used so far. So after the potential name list, you have this overlap name list. This is called overlap because we can interpret this as a many-body overlap between a beryllium-11 wave function and a beryllium-10 wave function, in the sense that was introduced last week by Jeff and Ed. Remember, they have these overlaps, and these can be approximated by a sort of single particle wave function. So this is what is done here. So we have two overlaps because we have two states, and each of them is labeled by an index, Kn. Also, we have to specify the partitions that contain. So we are doing the overlap, we have to identify the partition where beryllium 11 is and the partition of beryllium 10. Imagine in a more general calculation, we might have many partitions for different channels. So we have to give the index of each of these partitions, and this is given by these IC numbers. Then the important thing, we have to identify, before that, if this wave function corresponds to the projectile or target, in this case, so In equal 1 is for the projectile, and these are N, Nn, S, N, L, and J are the quantum numbers defining the ground the bound state. So we have, for the ground state, Nn equal 2, according to the labeling of Fresco. This is the 2s state. L equals 0, J 1/2. So this J here is the result of coupling the L with the Sn, with the spin. So we couple the spin of the valence particle with the orbital angular momentum L to give a J 1/2. This KB pot is the index of the binding potential that will be used to produce this bound state. So remember that we decided to label this with 4, with Kp equal 4, so we identify this in this name list with this variable. Then the separation energy, that is 0.5 MeV, and this maybe we can discuss this afternoon. And the same for the excited state. So now the quantum numbers are 1 p 1/2, 1 p 1/2. We use the same potential, but we change the separation energy. So this is the information required to generate these bound states. Now we need to, so we have defined already some two bound states. We have now to tell Fresco that we want to couple these two bound states with this single particle model. So one thing is the structure part. Now we have to put the dynamics, the kind of couplings. We could have defined this bound state to do a transfer calculation, for example. So now we have to tell Fresco that we want to couple them with a sort of single particle or cluster excitation. So this is done in the next name list that is called coupling. So the coupling name list specifies the kind of coupling between the different states that have been generated. So kind equal 3, you have a list of, I don't know how many, like 8 or 9 kind of couplings. You can do many different things. So kind equal 3 corresponds, you look at the manual, to single particle excitations of the projectile. You are doing excitations of the target, is a different kind. This kind equal 4 actually. Then we had to identify here the partitions containing the nuclei that will be excited and the core partition. So these two variables, IC2 and IC from, corresponds again to the partitions. So the second partition is the one of the core, the first partition is the one of the excited state. And then this IP1 is the maximum multiple for the coupling potential. So remember that our coupling potentials contain one lambda that corresponds to the multipolarity. So we could include 0, 1, 2, whatever. So at some point we have to stop. So this is the maximum multiple that will be included. So Fresco will include in this case from 0 to 4 multiples. Again, this is something that we can check afterwards. So we can set IP4 equal 1 or 2 and then increase until we get converged results. And finally, we have to give the fragment target. So fragment is the valence particle and the core target potential. So this is specified through these variables that point to these indexes for the potentials, to the Kp indexes. So remember that we decided that the valence target potential would be number 3, so P1, 3, and P2 corresponds to the core target potential, that is the beryllium 10 target. I know there's a lot of variables, but well, you will have this slide this afternoon with you, so you just can go there and try to modify according to the example that you will have to do. Right? This is just a rough explanation. And finally, these are the spectroscopic amplitudes, because remember, in general, every time we define an overlap, you have the composite system, the core, you make the overlap between this wave function, and this is represented by some spectroscopic amplitude times some unit normalized wave function. So this spectroscopic factor is specified in this name list. So this CFP is, so IN again identifies projectile or target, IB is the index for the state of the composite inside its partition. So now we have, in beryllium 11 partition, we have two states. So the first one will be IB equal 1, the second one IB equal 2. And that is why we have two of these name lists. So IB equal 1 corresponds to the ground state of beryllium 11. This is the state of the composite. IB equal 2 corresponds to the beryllium 11 1/2 minus state. IA is the state of the core. We have only a single core, so it will be always 1. Kn specifies the wave function, the overlap that will be used for this overlap. So we have defined what is the state of the composite system, the state of the core. So we have the overlap between these two objects, and we want to tell Fresco that the result of this overlap, that will not be calculated with Fresco, we will approximate this by spectroscopic amplitude, this number A, times a wave function, and this wave function is identified through this Kn index that corresponds to the index that we chose for the overlap function. So this overlap is where we calculated already the wave function. So here we are identifying the wave function of the state. We have 1 for the ground state, 2 for the excited state. And in the single particle picture, so all these calculations are probably only sensible within the single particle picture. The spectroscopic factor strictly should be 1. For transfer calculation, it can be smaller, larger than 1, but for this single particle excitations, typically it will be 1. That's all. I think that it's enough for today, and after all this material, then you will see some, after the coffee, some illustrations by Filomena, and this afternoon we will try to do some homework related to this subject and to build some input for these cluster models. Okay?